Okay, when we say cell permeability, means close what? What's the barrier of a cell? Cell membrane, right? Not cell wall. Cell wall is with a hole. Cell membrane penetration. What's the thickness of a cell membrane? 4 nanometer. So if we amplify that billion times, that's 4 meter from here to there. Water molecule like this, like 20, 30 centimeter, like this is water molecule. So this molecule needed to penetrate that much. Water is too hydrophilic. Lower P of water means minus value. So very hydrophilic. So here is the phosphate group, there phosphate group 2. Water just come here and just bounce here. Cannot penetrate this lipid area. Fatty acid, it comes in, long tail can go in, but hydrogen just stay here, it cannot penetrate. Hexane, organic molecule, is also, maybe in water media, hexane may form just a oil bubble. So it cannot penetrate. Or it goes in, but it just stay in and stay. It cannot move. Ethanol. Ethanol, it has 2 carbon. Actually, it can be 1 OH, not super strong hydrophilic. This kind of go in and out. Ethanol molecule in and out. And time to time, some of them can penetrate, go in there. So ethanol can go everywhere, every membrane in our body. Even it can go to the brain. Even can penetrate the BBB. So that's why methanol goes into the membrane, make the membrane a little loose. You can feel it, right? If you drink, then we feel like our membranes are a little loose. Right? So the signaling pathway, every structure is a little loose. So ethanol is kind of molecule in balance, reasonably hydrophilic, hydrophobic. So C log value wise, less than 2 penetrate not very well the cell membrane. C log value should be less than 5, bigger than 2. That's kind of a reasonable range of the cell permeability. There were 2 kinds of parameter, right? One is a pharmacokinetic parameter, the other pharmacodynamic parameter. Kinetic, dynamic, in a sense, is a similar word, similar meaning. Just redefine it. Okay? Pharmacokinetic means how our body treats the molecule. Okay? So whether let them come in, distribute, metabolize, and excrete. That's how our body treats the molecule is pharmacokinetic. Pharmacodynamic is whether the molecule, how it affects our body, whether good effect or bad effect. Bad effect we call toxicity, good effect we call efficacy, potency, kind of good things. Okay? These are all pharmacodynamic parameters. So 2 aspects we see. How the molecule can come into our body, pharmacokinetic. Pharmacodynamic is what kind of effect the molecule has on our body. So those are 2 effects and 2 parameters. Potency and efficacy is not same. It's a little different aspect, right? Toxicity is a negative value, and pharmacodynamic includes the potency. It is not. Admin A, absorption, D, distribution, okay, M, metabolism, E, expression. Come in, distribute, change, and move, remove. Okay, those four are admin is pharmacokinetic parameter. The T is also quite important. Sometimes they combine it together, but toxicity is not pharmacokinetic, it's a pharmacodynamic parameter. Okay, good. So if you look at here, you can count the the hydrogen atom. 1, 2, 3, 4, 6, 10, 11, 11. So it's between 12 to 20. And hydrogen number you count will be about 15. Then 10 of them maybe this size approximately. Glucose molecular weight 180. And small molecule definition is smaller than 500. So that kind of approximate number is good enough. Okay, good. So this molecule, comparing to its size, it has a hydroxy group, NH group. It has relatively a little more hydrophilic groups. So 2 to 5 is kind of reasonable range. C log P, what is P? Partition coefficient between one is N-octanol, the other is water. So organic solvent and water. We have partition coefficient. You could use maybe hexane, which is a common solvent that we use. Then hexane water is too much different, so they may be fully separated. They may be difficult to share the molecules. So octanol, a little long chain, but at the end, hydroxy groups. So this choice, you can make arbitrarily any combination you can choose, but this is kind of the standard method. So N-octanol has a little contact point with water, but relatively hydrophobic on one side. So if you see log P value is, what is the C? It's a calculate. So real log P value is we need to do the experiment. So 1 liter of N-octanol and 1 liter of water, add to the molecule and isolate them, evaporate, and measure the amount. You can imagine it's quite a lot of work. So for every molecule to do that, it's a little too much. Of course, some of them we do experimental measure, but it is not made really for just a design molecule. Approximate number we want to know, then we just put it into the algorithm and let them calculate. Approximate number, calculate with log P. Okay. So ChemDraw is a common molecular structure drawing software. So ChemDraw, if you draw the structure, it can calculate this log P value for us. May not be 100% correct, but maybe with a 10-20% error range, it gives us reasonable the property of hydrophobicity. Okay. So hydrophobicity 2 means octanol versus water. What is the ratio? 100 to 1. Okay, that's a 2. But this log is log 10. Okay. So if it's 1-to-1 mixture here and here, then the molecule is hydrophobic or hydrophilic? It's a very hydrophilic. Okay. 1 to 100 is still, that's kind of a borderline. Okay. To penetrate the cell membrane, 1 to 100 is kind of a low borderline. 1 to 100,000 is kind of high borderline. Okay. If it's higher than that, too hydrophobic. This is 0. 0 means 1 to 1, right? So it's low value, so 0 means 1 to 1, that's too hydrophobic. Okay, it's 2, 1 here, the other one here. Okay, 2 hydrogen bond donor, proton source. CH, we don't count. There should be hydrogen bonding forming one, attached to N, attached to O. How about attached to F? Hydrogen bonding N, O, F. Isn't it? So how about the F?
Well, if it's too much.
No. The only one, too much is good for the hydrogen bonding forming. The only one which can form hydrogen bonding is HF. If F is attached to carbon, then there is no directly attached to F, right? That's why there is no other hydrogen bonding forming F containing carbon. So hydrogen bonding, we only count the N and O. It's also definition-wise, below there, P and S, they are a little more electronegative than carbon, but in this definition, we don't count it. It's defined by the guy, what's his name? Lipinski. He is the medicinal chemist who tried to collect the data from the commercialized drugs, hundreds of thousands of drugs, and he analyzed these and generated the so-called Lipinski rule, or Lipinski rule of 5. A lot of 5 there, right? So hydrogen bonding donor number wise should be less than 5 to be good drug. Okay. C log value wise between 2 and 5, hydrogen bonding donor less than 5. Okay, that's 3. 1, 2, 3. That acceptor means it can take proton like this. Okay. It's not hydrogen atom, it's a proton, H plus. Okay. So hydrogen bonding donor wise, acceptor wise, how many hydrogen bonding acceptor allow? Less than 10. 2 by 5. Okay. Because usually the acceptor number is higher than donor. Any N number or number is acceptor number. Okay, it's a 4. 1, 2, 3, 4. Not 5. So rotation number wise, how many rotation number allowed? That's also 10. Less than 10. One million cells you studied. If you And 10 micromolar of this drug. What's the definition of this? Sorry, 10 micromolar. Without any the drug compound, it can go up to 4. So by adding the compound, you got half of this. This concentration is what? Gross inhibition 50. Okay. So you started with 1 million, but if you broaden, 4 million is the maximum number you could get. But the growth is inhibited by half. That's GI50. That's the definition. Lipinski rule, those numbers are pharmacokinetic parameter or pharmacodynamic parameter. Dynamic? Kinetic? This, the Lipinski rule tells what? This tells whether the molecule can cross the first barrier of this cell membrane, right? Is that kinetic or parameter? The kinetic or the dynamic? It's a kinetic. Only first barrier. There are many different reasons why it cannot reach to the target, right? Pharmacokinetic parameter means whether the drug can go and reach to the target molecule or not. That's a pharmacokinetic, right? Only one barrier. So definitely this is a pharmacokinetic parameter. Whether it binds to the target very well or not, or kill it or not, we don't know. That's a pharmacodynamic parameter. Okay, okay, this is a GI50. Now same condition, you add the 20 micromolar. And then the end position is 1 million. You are starting cell number to 1 million. You could go to the 4 million. So by adding inhibitor, the end point is the 1 million. Okay, that is what we call TGI50. What is that T? Threshold. Whether it's go over or not, because that is the starting point here. This is TGI50. So this may imply that this compound is now cell toxic. This compound is just a block the cell division, possibly. That's why the cell number was not changing. Doesn't kill it, but just let it stay. In antibiotic, we have a bactericidal. Cidal means it's killing. Bacteriostatic means it's let it stay. So kind of a concept. So that's a TGI50. One more definition. Now add a little more. Oh, sorry, this should be 0.5. You started as 1 million cells, and it becomes a half million. That is LC50, lethal concentration 50. So that's kind of actually killing those starting point of the cells. I started with 1 million, now I got half of them survive. That's LC50. Now, last time we learned about the LD50, lethal dose 50. So what is LC is a concentration, dose, usually dose unit is milligram per kilogram by weight. LC50 usually we call like this unit, micromolar or nanomolar. Of course you can convert it to each other, but this is more chemical weight. And milligram per kilogram is more physical weight. Okay. That's dose and concentration. in other terms, this can be defined as analytically too by calculating membrane. And IC50 is an inhibition concentration 50. That's usually used for enzyme activity, kind of a small scale one. Right now we are talking about the whole cell survival kind of things. Die, grow, or not. Okay. So these three parameters has been used in NCI 60 cancer cell line compare program to have the idea what's the mechanism of one compound. That's something I tried to explain in the video. And NCI 60 system, they use a 60 cancer cell line. Cancer cell line, that's why that's a 60 dimension. But from one set of experiments, you could get 3 values. By giving different concentration test, you can get 3 values. That's why 180 data point could be collected for one compound. 60 different cancer cells, they are representative for lung, liver, muscle, muscle is not cancer, brain, blood, different kind of cancer cells they collect here. Each cells, they may have different reasons why they become cancer. Today we are going to study about the first chemotherapy. If new compound can attack different cancers with a different efficiency, different efficacy. And those values, those relative values can be given. So one compound, if you test a different concentration, you could expect 3 values each. Then one compound can generate 180 different property parameters. If those parameters is very similar to each other, then they may have a similar mechanism. I will explain that again later. Backup is very important, but I was not sure whether you guys could get the idea of that. Now after NCI compare program, I try to do some connectivity there. In connectivity map, the measurement was gene expression level against all our genes. Our gene may be 25,000, so exact number is not important. Okay. The gene change, if you give one compound to the drug, to the body or cell, and then how those 20 genes are responded to. So that's kind of very big dimension of the data. If their pattern is very similar, then you can assume this compound and this compound may have a similar mechanism. That's the idea, how we can analyze the mechanism of the compound. Okay, so based on this, we just move into chemotherapy today. Okay, this is the anti-cancer drug 1, chemotherapy. And first thing is whether the drug can, this drug we call small molecules, whether this drug can go into the inside the cell. After penetration, and whether it can go to the further to its target, that's the next study. Okay. Anyway, for this, we need to cross the plasma membrane, and several things to consider. If it is live cells, live cell membrane has a potential. We mentioned that before. And inside, outside, those structures are different. Inside is more negative. Inside is more negative than outside. In both of cases, in any cases, both sides are negatively charged. Then, negatively charged drug. The penetration of the cell membrane is favored or disfavored? It is disfavored because of the negative repulsion. Negative charged molecule across here and just bounce and not penetrate. Positive may be better than negative. At least the approach to the surface is okay. Next step is penetrating this value. Now it counts those C log P value is important. whether it can penetrate or not. So this one we practiced together, and that partition coefficient was about 2, a little less, but this is the approximate number. So 1.9 failed, 2.1 success now. It's kind of around that range. Okay, around that range. That's okay. Then question 1. Okay, the rotation. Here, why this does not count? Why this does not count as rotation? Here, if this is rotating, then whole OH group is rotating together. It's kind of a blocking factor, blocking effect there, right? Any materials come in, and this whole OH is rotating. It has this kind of a blocking effect, can bounce. But if this is rotating, this H is just a dot, right? Atom. Even though it's rotating, we don't feel that bulky effect. That's why we don't count it. Similar way, CH3 here, this rotation, it has this propeller rotating, big effect here, rotating. But this is CH, we don't feel the effect of rotation. That bulky means it's an electron cloud. Whether electron cloud maybe this is shield or not. Okay. So that should be straightforward. Aspirin. Let's spread this very quickly. Aspirin is slightly higher than 2, maybe okay. And this molecule hydrogen in what number? 1. Yeah. Okay. What's that term? 4. Rotation? 5. We don't count this. Double bond we don't count. Okay, only single bond. 1, 2, 3, 4, 5. If it is in the ring, we don't count. Okay, rotation 5. This molecule drop like or not? So molecular weight given here 180, similar size to glucose. Small enough. Pass. Okay, this molecule pharmacokinetically, okay, it can penetrate the membrane. It does not mean that it has effective drug effect, right? It can go inside the body. That's all what the institute says. Okay? Almost one thing. Thalidomide. Maybe you may have heard these two isomers. One is effective one, the other one generates the malformation of the baby. Okay? But molecular structure was exactly the same. These are stereoisomers. Enantiomers, physically the same, but differently behave in the body because our body is chiral. Okay, now, this molecule, partition coefficient almost the upper limit, the molecular weight is less than 500. Hydrogen ion donor, 1. Accepted? 6. 1, 2, 3, 4, 5, 6. Rotation? Interesting, it's only 1. So the molecule is bound into the ring structure, then usually you can suppress those rotations. So this molecule, pharmacokinetically, it may have good penetration effect to the body. Okay, let's see. Now here, why rotation bond if it's more than 10? What's the problem? Okay, let's look at this molecule. What is the rotation number on this molecule? Yes, I think I come to 14. I don't know. Okay, right? Let's come together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, with many rotating bonds. Now it is rotating here, making this graphene. It's rotating here, making this graphene. It's also here. It's kind of moving like this. So then, crossing this barrier, okay, even though this value is, let's say, it's marginal, but if this molecule, the two penetrate there, making this sharp and go in, or moving around, okay, this kind of the rigid shape may be better to penetrate there. So that's why with the flexible molecules, usually it's not favored to penetrate the cell membrane. Now this is Taxol. Some of you chose this molecule. If you can solve this problem, a rotation number of this, let's not do this here, but I will give you this in the lecture note. You can practice on your own. Maybe you see this molecule in the bottom. So if you can count this number a little too much, then you can solve the problem. By the way, rotation bond of this definitely more than that. Molecular weight much higher than 500. Hydrophobicity is okay. Hydrogen bonding donor, how many donor here? Isn't it 5? We don't count this? Okay, we don't count that. That's a carbon. 1, 2, 3, 4. Okay. Donor number okay. Acceptor number? Definitely more than 10. Okay. Acceptor number, molecular weight, rotation bond, it's all off. Still, this molecule is being used as a quite important anti-cancer drug, flexible molecules. It has a unique mechanism, and it's not very well soluble. That's why sometimes we make it like chunk and just put it somewhere. It's slowly releasing and prevent the cell division type of things. It's not ideal case, but that mechanism is quite unique. That's why still, sometimes even though, despite that very bad property, pharmacokinetic property, if the pharmacodynamic property is excellent, still, if you don't have other choice, then that's kind of extreme case. So based on this, now today's topic is cancer treatment. If you have cancer, first of all, what is cancer? It's unregulated, fast growing, and all of those cells and tissues which they should have their own function, and then it should keep their proper size. Sometimes it overgrow. It should not grow too much. If it's very small, then it's difficult to detect whether it's just a spot or cancer, we don't know. But if it becomes like this size that we start to worry about, it's a little too big. If it goes to this level, then definitely there's something wrong. Either that's a malignant or benign, upsum or yangsum. Either way, now it's a problem. Right? That kind of unregulated growth of the tissue is in general defined as cancer. And now the cancers have some the unique properties. And first of all, those signaling for the proliferation in DNA level is spreading out. Mutations are accumulating. And they resist to the suppress. Hey, don't grow too much. Keep your size. They don't listen to you. And then they keep dividing. Make more numbers of cells. And not only just growing, invade different tissues. That defines whether this is a benign or malignant. They have separating each organ. So don't come back. But if each tissue has its own boundary, and there is a basal membrane to isolate it. So here, angioma. Okay. So if that growth is penetrate to that, then that's dangerous. It's invading. Then we define that as malignant. If it just grow inside there, even though size is very big, usually we call it benign. Okay. Whether it's invading different tissue or not. Okay. That's invading is important. And if that becomes very big tissue, then problem is it does not have a good supply of oxygen as a nutrient. That's why they recruit, make new blood vessels inside there. So-called angiogenesis. Angio means blood vessel, genesis means forming. Okay. New vessel, abnormal new vessel is formed into the tissue. And they resist to die. They don't want to die and live forever. So this is kind of character of cancers. For those cancer treatment, we can define the different the growth. Normal cells like this size. Grow means two ways. Cell size becomes bigger, or cell numbers becomes bigger. So cell size becomes bigger. Hypertrophy, trophy means nutrient. Hyperplasia, the number is increasing. Hyperplasia. what is the typical example for this? You may have heard liquid cells here. It's not cell number increase, cell size increase. Okay? But most of those other parts of the body, due to the cell number, is increasing. So this is still expectable normal case. In cancer case, this hypoplasia is too much. Neoplasia, okay, making too many cell division of the product. And also they have strange shapes, mutations and shape, and also the nuclear number, they become so different. So neoplasia and dysplasia is abnormal. So this is what we call like the cancer cells. Okay. This is just obesity. This is just overgrowing. Okay. Now for that, if we have that kind of things, that kind of unwanted the tissue formed in our body, maybe first treatment you can think, cut it out, surgery. Or we can get radioactive radiation, X-ray, gamma ray, and radiation. Chemical treatment, that option is because we can use a drug. And those drugs also we have different kinds. As we are studying right now, small molecule drugs, or biological materials, signal-like hormone or proteins, or maybe whole cells, cell therapy. So today we are going to focus on this part, and that kind of first generation anti-cancer drugs, those are we call chemotherapy. Chemo means chemical therapy. When it says chemical therapy, next generation of the drug is also small molecule, but usually if you say chemotherapy, utilizing active chemical against fast-growing cells. And coming is going to introduce those a little more details for this topic. Coming? Okay, please welcome them.
Hello, my name is Kami, and I will talk about chemotherapy. The index of contents is as follows. Among the top 10 cancers based on projected in 2024 in America, the number of cancer patients increased in 6 parts. This is why research on development of anti-cancer drugs is important. Anti-cancer drugs can be classified into these 3 categories. First generation of cytotoxic chemical anti-cancer drug, second generation of targeted anti-cancer drug, and third generation of immune anti-cancer drug. Among them, I'd like to talk about first generation of cytotoxic chemical anti-cancer drug known as chemotherapy. First generation chemotherapy drugs are typically the first prescribed to the cancer patients upon diagnosis. These drugs directly target rapidly dividing cancer cells, distinguishing from normal cells. These are the representative chemotherapy drugs. So chemotherapy drugs can classify into these 3 categories: alkylating agents, antimetabolites, and natural materials. First of all, alkylating agents are chemotherapy drugs that binds to DNA and causing damage or destruction to its structures. They interact with negatively charged sites on nucleic acid and form cross-links, thereby damaging DNA. They inhibit the growth of cells and induces cell apoptosis. Representative drugs in this category include cyclophosphamide and cisplatin. Second, antimetabolites exert the effect by inhibiting the metabolic processes necessary for DNA replication and cell survival. For example, they hinder nucleic acid synthesis by utilizing purine or pyrimidine analogs, which interferes the synthesis process by incorporating instead of nucleic acid. It mainly acts on the S phase of the cell cycle. Representative drugs in this category include pyrimidine analogs such as 5-FU and capecitabine and gemcitabine. These are the structures of purine and pyrimidines, and you can easily know that these structures are quite similar. So we can use, our body use these instead of the nucleic acid in the synthesis. Chemotherapy drugs derived from natural materials exhibit a variety of pharmacological actions, including microtubule inhibition, topoisomerase inhibition, and anti-tumor antibiotic activity. Microtubule inhibitors are exemplified from plant-derived alkaloid compound. The taxane family is a prime example. These drugs exert the effect by targeting microtubules during cell division and inhibiting their function. Microtubules are a crucial component for the cellular cytoskeleton involved in cell division. Disruption of microtubule structures can lead to various diseases, including cancers. Paclitaxel and docetaxel are representative drugs in this category. To explain in more detail, paclitaxel acts on the N phase of the cell cycle. With a strong affinity for microtubules, it enhances tubule polymerization within the spindle apparatus. Disruption of the normal process of microtubule connection leads to the formation of abnormal microtubule structures, causing the loss of the spindle polarity. Consequently, immature chromosomes are generated, interfering with cell division. Topoisomerases are enzymes for relaxation of the double helix of DNA, which is crucial for DNA replication and cell division. Inhibition of topoisomerases leads to DNA damage and ultimately cell death. Topoisomerase and irinotecan are the representative drugs in this category. Also, in addition to cancer cells, these anti-cancer drugs chemotherapy drugs target rapidly dividing normal cells, such as hematopoietic stem cells in bone marrow, hair follicles, and epithelial cells, leading to side effects such as leukopenia, alopecia, stomatitis, diarrhea, severe nausea, and vomiting. Thank you for your attention.
Could you classify those chemotherapy according to mechanism? You had this category. Let's just say our target is the fast growing cells. And then what kind of a category of the drugs for the chemotherapy has been introduced here? Can you point out?
DNA inserting some chemicals that similar to the nucleotides so that it can.
So inserting something into the DNA. Let's think about the strategy. Last week we had antibiotic. We targeted something unusual. cell wall, which we don't have, will attack that one. And DNA synthesis, protein synthesis, because they have a different ribosome from us. Now, this week, our target is fast-growing, unregulated, fast-growing cells. Which side we should attack? Okay, that's the question. Fast-growing means they need to make more DNAs because they need to amplify. Each cell has how many DNA? 1N, 2N, 3N, 4N. How many DNA each cell has? One copy from father, one copy from mother. Every cell has a 2N DNA. If they cell want to divide, they should make exactly same amount of DNA they should make, right? DNA synthesis should be fast. And to make this cell size, they need to make more proteins too. They need to absorb a lot of nutrients, make proteins, almost the same amount of protein. If not, one cell is this size, the other cell is this size. They wanted to have regular size of cells they want to make. Those kind of character is fast growing cells property. We need to attack those positions. So, inserting something into the DNA. How can you insert something into DNA selectively only to cancer? How can you insert the chemicals selectively only to DNA of cancer, not normal cells? What's the difference between actively growing cells in DNA and normal cells? Speed of synthesis? Cancer cell needed to make the DNA, it's more open than normal cells. It's more euchromatic. Of course, it's fast, but why this is more accessible to the chemical compounds? Because it's more open. It's a condensed form, epigenetically condensed form. It's kind of protected. It's more open, that's more vulnerable, that's more accessible to any small molecules. Now, if you look at this alkylating reagent, first one, that's chemically reactive ones. And those are nucleophile or electrophile. 동원이 배우는 다 이런 인생이지. You know what nucleophile and electrophile means, right? You don't may know. Those alkylating reagents, they are nucleophile or electrophile. That's electrophiles. That means in our body, or in DNA or proteins, we have a lot of nucleophiles, but we don't have much electrophiles. Nucleophile, NH, SH, OH, those kind of things are nucleophiles. I can highlight, again, attack, nucleophile attack here, and then make a covalent binding. Those are chemically reactive electrophiles. If you add electrophile, which can reach to the inside the nucleus, penetrate the first membrane, plasma membrane, and go into the nucleus. If it can attack, insert into DNA and make a covalent binding. Those are alkylating reagents. Alkylating means we add reactive electrophiles to the target. Okay? Of course, those molecules are very toxic. It's a chemical reactor. That's a chemically reactive materials. So those were first class. Second strategy is they need to divide. They need to collect the nutrients. They block the synthesis of those materials, or blocking those provision, delivery of nutrients to the target. So inhibit those building block synthesis. That's the second strategy. So the strategy is interfere with their cell division. For cell division, they need to make a DNA, they need to open the DNA, and then make a copy each. Right? So that process is one. The other process is they make chromosome and then cell should be divided, and that is catalyzed by this machinery, so-called microtubule. Microtubule is one of those cytoskeletal cells like this shape, and microtubule is usually suspending to the outside like this way. And there's another protein structure, it's pressing from the surface to the inward, those actin structures. Actin suppress this way, microtubule push out like this way. Those two balance make this cell shape. And when the cell divides, this microtubules dynamically change. In one direction is growing, the other side is disassemble and then getting shortened. The dynamics is very important. So one target is attacking this microtubule two ways. One way is stabilize too much, don't let them move. Or unstabilize, destabilize. And the microtubule is disassembled fully. Both ways, that the microtubule function is suppressed. Taxol is overstabilized. Taxol bind here, and this disassembly doesn't happen. It's just stable, and just same shape for a long time. Then they cannot divide. Vinblastine, nocodazole, colchicine, those are just disassemble everything. There is no microtubule available. They cannot divide. So this is the one stage, attacking microtubule. The other approach is attacking this mechanism, open rewinding, changing of those structure, either 1 ton or 2 ton, that's so-called topoisomerase. Topology is changing to make this superhelix. Open gyrase, clip and then reconnect, changing this the ton is a topoisomerase. Those enzymes, if you interfere, then the cells in the middle of the DNA synthesis, they cannot finish their synthesis. So I said the 4 things: alkylating agent, supply of metabolite, metabolism blocker, and cell division. Cell division 2 ways: attacking microtubule or DNA machinery. Okay, these 4 are main mechanism of chemotherapy. So based on this, I add up a little more. So the character of cancers, first character is this kind of fast cell growing, and during those cell growing, in the regular status, the chromosomes, DNAs are spread out. When they need to divide, they assemble, and then make a copy first, double copy, and then they form out this kind of a chromosome, assemble the structure, aggregating the structure, very well aggregated structure. Okay? And they align in the middle, and then those machinery attach and then withdraw. These are microtubules. If you inhibit this stage, DNA synthesis, or interfere with this stage, then the cell cannot divide. So during this process, so we call this is a cell cycle. In regular state, we call it G0. G0 is dispersed, that's a live normal life. I don't divide, I do my job. I'm muscle cell, I'm nervous cell, and just I am happy with my neighbors, and just don't die, and let's live together for long. Once they get signal, okay, I need to grow, then they enter this status. Getting some growth signal from outside, okay, we need to make more cells. Then they go into G1 state. G means gap. Gap 1, gap 2. Okay, first thing is collect materials. Eat a lot. And collect enough amount of ATP, GTP, DNA synthesis building blocks, protein synthesis building blocks, amino acids. If I don't have enough material, then collect glucose and then make more amino acids, make more nucleotide building blocks. So metabolite blocker is blocking here. Don't let them collect more materials. Okay? So cell division is, in a sense, is the most important the function or function of the one cell. It's almost like making new baby. I need to make exactly the same copy of myself. To do that, I need to get almost the double size of materials. Then I can make the 2 cells. So G1 is that step, collect all the materials. That means in G0, they don't do that. They don't need much. Okay? When they want to make a copy, then they collect a lot of materials. And then they check everything here. And there's one checkpoint. Okay, I have enough material to make DNA copy. Protein amount is enough. Then if they say yes, if checkpoint is clear, then they go into S. What can be S? Synthesis. DNA synthesis. Start. Now they start to make DNA. DNA is the most important genetic information. So it cannot start at any time, and it cannot stop in the middle. Once it starts, they should finish. Okay, that's why this is quite vulnerable state. So they make synthesis of the DNA. If the synthesis is finished, then they check one more time. Can we really divide now? And those new strand of DNA is intact and complete. The kind of checking is G2. If that checking is all cleared, then actual cell division happens. That's the so-called mitosis. Right. During this whole process, DNA content is changing. Right? Then if you draw those DNA contents, you can draw this way. Now this one, 2n state, maximum number it can reach 4n state, double copy. Right? In G1 state, it's still same 2n. In S stage, it's increasing, reach the maximum of 4n. G2, it should stay same 4n. Before cell division, it's keeping 4n. And when cell divide, it's becoming up. Overall. Right? If you can monitor those DNA contents, then maybe we can tell which stage of the cells are. Right? So here, what do you need to measure? DNA concentration or DNA number. To do that, we add DNA intercalating reagent. This can bond to DNA evenly and generate fluorescence. If we can measure those fluorescence amount, then we know which stage of the cells are. So to do this experiment, we usually use this kind of machine, flow cytometry. Flow means it's flowing. Cytometry means cycle the cell, metry means measuring. Flow the cells one by one, like this. And then give the light. And then if this light hits this cell, it generates scattering signal, or it is labeled with the fluorescence material, it generates fluorescence signal. They can tell fluorescence amount. If DNA content is high, then it increases. Now here, y-axis is the cell count, cell number. X-axis is the DNA content amount, measured by fluorescence material. Here, this is 2n state. 2n state is a moderate of the cells are there. If it becomes increased, then S phase, and then this is 4n state. If there is any, then you can divide this 3 layer. That's why you can divide. Then this is G1. This is the S phase. This is the G2n state. Okay. So this kind of flow cytometry data can tell us what percent of the cells are in G1 state. And here, if it's smaller than this, half of that, which can have an N. What kind of a cell has an N? Hmm? Stem cells 2N. Gamete cells, sperm or egg cells, they have 1N, right? If it's not sperm or egg cells, this should be cell fragment. It's a broken cells. Okay. So then, now using this information, you can tell what's going on, kind of which state of those cells. Now this is real data. So this is a model, and then if you inject the growing cells, even though it's fast growing cells, majority of them are in stage G1. S stage is relatively small because that's very vulnerable state. They don't want to keep S stage too long. Right? DNA synthesis is a very dangerous stage. If it's inhibited in the middle, then they can die. So finish up quickly. Even though this looks long, but cell count is low, means not many cells are in S phase. And then wait here, that's G2. Check whether everything is okay or not. If it's okay, then divide, then go back here. Okay? Because this count is a cell by cell count. That's quite useful technique. So for the flow cytometry technique. Now here, if you add compound, drug compound. So this compound, even though you don't know the name or function, by looking at increasing those concentration, what happened? Which population is increased? G2M is increased, G2 was increased. DNA synthesis was okay. After DNA synthesis is all done, now they needed to go to cell division, mitosis. They could not go into the mitosis. What could be the function of this molecule? Either topoisomerase inhibitor. No, it cannot be. Topoisomerase inhibitor maybe start here, right? Most likely this is microtubule effect. Either overstabilize or destabilize. Microtubule cannot separate these two. That's why every cell has a 4N state, but they accumulate stopped there, accumulated here. Okay. How about this? This is regular. And by adding drug compound, you see this effect. What can be the mechanism of this cell? This is a topoisomerase, DNA synthesis blockers. They are accumulated in S phase. Okay, this is S state compound. So last two stage, microtubule and topoisomerase. If you use a metabolite blocker, what happens? They may stay in G1. They cannot go into the S. They do not collect enough materials. Alkylating reagent, you may start to see these populations. Cells are dying because it's a damaging and cannot survive and fragmented, go into apoptosis. Okay. So this is what we can expect using those 4 classes of drug compounds. Okay. First generation of anti-cancer. Now this kind of image you have seen before. This is measuring those inhibition. This activity here again. Activity goes down. This is the inhibition test. So here IC50 is concentration. One of those questions. To make the good drug, do we need to increase the potency or efficacy? What do you think? Now let's check quickly again the definition of the potency and the efficacy. These are two, ED50 value here, compound A and B. These two compounds, how do you compare? A is more than B by what? A is more potent than B. Maximum activity is the same. A is more potent than B. What does that mean? You can use a small amount to get the same effect. Right? To get a good drug, small amount you can use, then that's better. Chance of getting side effect is lower. Right? So that's, of course, that's the beneficial. That's the potency. The other factor is the maximum effect is different. Right? One compound that has high effect than the other compound. A has higher efficacy in this case. So that means small amount of the material can get maybe higher amount, but you should be careful. You have a high fever, 40 degrees. Our normal temperature is 37. So you take the anti-fever drug. If there is a very high efficacy, it drops your temperature down to 30. That's dangerous. So then you need to think how much of effect do you want to get. Maybe D is a safer drug. It does not go over too much. But amount-wise, it's better to have small amount. Okay? So potency is important. Efficacy sometimes you want to high, but sometimes it's safer to have a little low. Okay? So So that kind of thing you can think. So this other example I gave you on video clip 2. So this is each line is one cancer cell line out of 60. The experiment you will see like 10 times each of drug addition. If everything is okay, this is maximum cell count. If you have the compound, then it can reduce, and then depending on those position, this is 100 if you assume, this is GI50 value you can count. TGI is the same on the setting, and then SC50 is here. 3 values you can get. And different compounds may have a different potency, right? That's why different potency compound, the absolute value may not be exactly matching. But if you keep average value here, and then which one is from average higher and lower, then you can get this kind of pattern. Then even though the absolute value is different, this compound, if you look at those patterns, they look quite similar pattern. Right? If there is a similar pattern, Taxol, I know the function. It's a microtubular packet. This compound is a new compound. I didn't know, just synthesized and tested in this panel. They look like similar to Taxol. Most likely, this compound is microtubular packet. So that's the idea of NCI60 configurability. Similar things we can do in gene expression. We don't know why those genes are changed, but by giving one drug, I got one pattern, 20,000 of genes pattern. I tested another one. If you have more and more data, big data, now we have those classified data set, and then you can divide those. Okay, Taxol is in this class. Okay, this one most likely microtubular packets. DNA topoisomerase inhibitors, and make some classes. New compound coming, just giving one experiment, you can get a brief idea which class they belong to. Of course, there can be totally new mechanism that may be outlier. Okay? But this is kind of the idea. If you have a big data, how you can access those functions. Okay? So now to get the avoid the side effect. Alkylating reagents, all of these, the chemotherapy, the drugs, they are toxic. So one idea is maybe giving some interval, not every day, after one treatment and maybe 2-4 weeks to recover from normal cells, not to lose the hair and other the faster dividing cells in the body. That's one way, but that's kind of a passive way to do. Maybe other better approach is do not attack vigorously the massive parties. Maybe a little more selective killing, utilizing one targeted approach or immune approach. That's what we meant. Today we covered this chemotherapy, first generation. Next week we will talk about the second generation, targeted therapy, and third generation of immunotherapy. Okay, that is going to come next week, and same way we'll have class next week. Any question? Okay, today, thank you. You did a good job. Next week is okay, see you next week, guys.